Hi guys, it's Daniel here, finally back from various trips for over like 9 weeks for summer camps as well as a visit to the East Coast for colleges. But I'm finally back now, so let's talk about something math. Today we're going to talk about Hall's marriage theorem, and it goes something like this. Suppose we have some number of boys, so I don't know how to draw people, that's good enough. So you have these boys, and then you also have some girls. Okay, girls have some longer hair, I guess. Alright. And let's say that each boy likes a certain subset of the girls. So for example, this boy can like these two girls, and then this boy can like, for example, this girl and this girl and this girl. This boy can like only this girl, and this boy can like these two girls. So the question is this: can we find a certain matching of one boy to one girl such that every boy is satisfied with his matching? That is, every boy is matched with a girl that he likes. And that is essentially the question that Hall's marriage theorem tries to answer. So let's think about what would be necessary in order for this to be true. So if we take a look at one boy, sure, we can match it to whatever girl he likes. If he doesn't like any girls, then we're already done. We can't do it because obviously that boy can't be matched with anybody. So sure, that's pretty obvious. Now let's take a look at two people. If we have two people, and here are the girls, and these two people only like one girl, so they don't like anybody else, then obviously we also can't have this perfect matching, because if one boy matches with that girl, then the other boy is stuck. So that's also not good. Well, what about three people? Three boys. Well, similarly, if three boys all like that one girl, we're even more screwed. But furthermore, if these three boys collectively only like two girls, then we're screwed as well, because of course 2 is less than 3, so we end up having one boy not matched up with anybody that he likes again. So in general, we have to have that for any subset of the boys, the set of girls, the collective set of girls that these boys likes, must have size greater than or equal to the size of that subset. So if we take these three boys, then then this boy likes this girl, these girls, this boy likes this girl, and this boy likes these two girls. So the subset of girls that these three boys collectively like is this, and 4 is greater than 3, so far so good. If we take a look at another set, for example this, then this boy likes this girl, this boy likes these two girls, so 3 is greater than 2, so we're also good. If we take a look at only this boy, well, this boy likes both these girls, 2 is greater than 1, so this is also good. So it seems like this setup satisfies this necessary condition. And the surprising part that is Hall's marriage theorem is that this condition is not only necessary, but it's also sufficient. If we take for any subset of the boys, the collective set of girls that they like is greater than or equal to in size, then actually we can always find a perfect matching. That is the statement of Hall's marriage theorem. So let's take a look at what type of problems this Hall's marriage theorem can solve. It may sound a little obvious, but it's actually very versatile. So suppose you have a piece of cloth, and this cloth is made up of n different colors, and each of these colors make up exactly 1 over n of its total area. So each color has an equal area in this entire cloth. And say you want to cut it up so that you got a piece of where each color is represented. So for example, you want a yellow piece, you want a lime green piece, a forest green piece, a blue piece, etc. So you're too lazy to actually cut this yourself, so you give it to your friend to cut. But the problem is your friend is blind, so he can't actually see where the colors, where the edges of the colors are. So he basically just cuts it randomly into n pieces, each of equal area. So the question is, even if he does this, can you associate each piece with a unique color? So for example, if he cuts it haphazardly like this, let's see how many pieces are 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, like this. If he cuts it like this, can we still associate each piece that he cut out with its unique color? That's the question. So given that we're talking about Hall's marriage theorem, and Hall's marriage theorem states the existence of perfect matchings, so matchings that pair each color to its unique square or unique piece of cloth, then obviously we should think the answer is yes. So let's try to set out proving that the answer is yes. And by the way, if we want to try to find the actual pairing, let's see if we can do that. We can do yellow here, blue here. Let's see, we can probably do green here, purple here, this shade of pink here. Let's see. We can do lime green here, red here, and regular green right here. Okay, so this actually works in my example. My squares are obviously not all the same area, but yeah, you get the idea. So how might we prove this using Hall's marriage theorem? Well, we have two different things. We have colored sections, and we also have actually cut out pieces. So this probably suggests that we should consider one side where the boys, let's say, and the boys are, let's just say the colors. Actually, no. The boys are the pieces of clothing, because pieces of cloth, since each piece of cloth has to associate itself with exactly one unique color. So the boys are the pieces of cloth, and the girls are the colors. Like so. So there's n of each. So let's take a look in how exactly, what graph we should think about. Now that we have the boys and girls, we have to figure out what relation is between them. In other words, what rule do the boys follow in liking the girls? So what rule should we use here? Well, if the boys are pieces of clothing and the girls are colors, I think it'd be natural to use the rule where the boy is connected, well, the boy likes all the colors that is on that piece of clothing. So for example, for this boy right here, for this piece of cloth, it would like the the yellow color as well as the lime green color. So for example, if this was the first piece of cloth, then it would like yellow and green, lime green, like this. And then for the next piece of cloth, you'd similarly draw the edges corresponding to the colors that is on that piece of cloth, and then we do the same thing for all of them. And this is good because then by Hall's marriage theorem, we can find a perfect matching. We can find a unique color for every single piece of cloth. So what do we need to do to use Hall's marriage theorem? Well, we need to verify the condition for Hall's marriage theorem. And the condition for Hall's marriage theorem is that if we take any subset, the set of all colors that these pieces of cloth cover has to have at least the same size as the number of pieces of cloths. So let's see if this is true. Well, let's say we choose k pieces of cloths, and we want to see how many colors they cover. Well, since each piece of cloth has area 1 over n of the entire thing, let's just say the entire thing has area 1, so each piece of cloth has area 1 over n, then the total area of these cloths is k over n. So what is the smallest number of colors that a thing of size k over n can cover? Well, since each of the colors also cover an area of 1 over n, then that means that if there were only k minus 1 colors that these k cloths cover, then these k cloths cover a region of at most k minus 1 over n area. But k over n is clearly greater than k minus 1 over n, so that's a contradiction. So in fact, k cloths always cover at least k colors. So that means this Hall's condition is actually satisfied. So that means we can use Hall's marriage theorem, and we can find a perfect matching between cloths and colors, and that means that each cloth can be uniquely identified with a single color. So we are done with this problem.
Hey guys, Zong here, back with another math video. Our last video was on derangements, so this video we're going to continue on with derangements, and we're going to prove a much easier formula you can use.